Good morning and good afternoon, scholars. Welcome back to geometry class. You have here Mr. Sniffen. Happy to see all of you today. We're going to have a quick lesson as we begin to come about finishing kind of this concept of volume. The last figure we're going to be working with today is known as a sphere. A sphere, essentially, or a ball, is an object we're all quite familiar with. If we want to go about talking about it in terms of geometry and how we would go ahead and quantify it, we're going to be working with another volume equation today. But let's take a look at some other stuff that we must consider first. We know that the sphere, based on our cross sections section, was just essentially like a collection of stacked circles, of stacked disks going up, getting larger and larger and larger till you get to the equator, or that line that goes around the circle or the ball at its largest point, and eventually gets back up to the top where we're back to infinitesimal, extremely small, that one singular point like we saw with just circles in general. With this sphere, we have to consider kind of the concept of a circle, or the definition of circle, which we described as basically like a two-dimensional figure where all the points are equidistant from the central point. And that when we have our circle, all the little spots on it are going to be the same distance, or equidistant, from the center location. The same thing happens in a sphere as well too. We can see, obviously, we have this perfectly curved surface, but if we were to imagine the ability to see through this ball, we can draw a line or a radius from each and every single point directly to the center point of the sphere, and they'll all be the same exact distance. This ability to be equidistant allows mathematicians to come up with extremely complicated theories about the universe and about the quantum as well too. But it's beautifully parsed. Everything is just so intricately spaced and equidistant that we can come up with a ton of different real life examples and theoretical mathematical equations. What we're going to be looking at today, though, is kind of just what volume is in regards to a circle and how it's going to relate to other objects. So first thing I'd like for you to do is to take down into your notes. We're going to use this example here. We're going to look and find our volume. Our equation for today is going to be a bit different than our other volume examples. Since a ball doesn't have that constant cross section, we're going to, similar to our cone example and our pyramid example, we're going to need some type of ratio in the front, and that's going to be 4/3. Since we're dealing with the circle, we're going to multiply it times that beautiful number of pi. And what we're going to be doing uniquely here is that we're going to take that radius value, that equidistant point from the exterior to the center point, and we're going to cube it, or we're going to take that value, say, of 5 and do 5 times 5 times 5, 3 times. So before we go ahead and create an equation, what I like to do is show you kind of how we're going to go about drawing a sphere. There's many different ways you can watch on YouTube. Lots of fantastic artists that do shading and can make the sphere look extremely three-dimensional on that 2D piece of paper. However, that's not me. I'm not this Mr. Art teacher. What I'm going to do is show you kind of the easy way to turn this into a three-dimensional object, and it's going to be similar to our cylinder. When we were drawing our cylinder, we knew that we had depth because we had a three-dimensional object. As opposed to making the bottom of our cylinder just a straight circle, we used an oval to kind of show some distance associated with it. What I like to do here is take this circle, and we're going to draw an oval through the center, nice and evenly spaced, and it's going to be slightly football shaped. We're going to have almost a little bit of a point to it. We're going to come here. I'm going to peak just above the line here, just in terms of proportions. We're going to be nice and flat. So just using little arc.
Just think of it this way. All you gotta do is tap it in.
And I like the rotation method because I can consistently kind of do the same position over and over again.
Provided you're still in good shape. All you gotta do is just tap it in. Just tap it in. Hey.
And if you use a lighter grain color, a lighter pencil, be easier to erase and things like that. If you use a newly sharpened pencil, you're going to have some slightly darker lines.
Tap it in now. Hey, just tap it in. Just tap it in. Just tap it in.
And toss in
Tappy. Tap, tap, tap.
the little curves on the inside to avoid those points. So, not the bestest circle, but so this particular example here, we have our diameter drawn, which is normally going to be what you'll see as a hashed line going through the center. Either you'll see something say like 10 centimeters indicating the actual length of it, or you might see a description on the outside with an arrow pointing in like we saw earlier in the week. To go about solving for the actual volume of this particular circle, what we're going to do is just insert our values. Since we have a diameter of 10, our radius is going to be what? Radius is half our diameter length, so our radius is just going to be 5. So for now, all we're going to do is basically go ahead and insert these values. We're going to do our volumes equal to 4 over 3 times pi times 5 cubed. 5 cubed is 5 times 5, or 25. 25 times 5 gives us 125. And now we're just going to go ahead and combine. There's a couple options you have here in terms of how you're going to write down this particular number. You can go ahead, punch everything into a calculator if you want, and get a nice long decimal value, or there's a couple things you can do as well. Considering we have this notion of pi, we saw when we talked about circumference and we talked about the area of circles, we want to keep that value, that symbol, because occasionally it can communicate back and forth with other details. What I'm going to do here is keep this notion of a fraction and do 125 times 4, which is equivalent to 525. Oops, sorry, 500. I'm going to keep 500 over 3 and multiply times pi. This fraction here that I have, I can just set as my answer. 500 over 3 pi would be equal to our volume, or what we can write down as 500 over 3 pi centimeters cubed. Always remembering that cube. That is one option that you can go with. You can also, of course, as I mentioned previously, go about just drilling through and punching it into a calculator. You might want to also convert 500 over 3 to just a straight up number, but we end up getting a repeating value times obviously another repeating value. And if we're going to start copying and pasting items back and forth into various equations, we're going to lose some of those intricate decimal values. And that's why sometimes it might just be easier to leave your answer as here. If you got a question like on a test or a quiz or something like that, of course I'm just going to tell you kind of what specific method to use. And typically that's going to be like rounding to the nearest 10th place with your pi symbol. Okay, let's take a look at another example here. What we have here in this beautifully drawn example is a cube, and we know this to be a cube because we have 3 same measured dimensions for length, width, and height. All 3 equal sides dictates we have a cube or the square prism. What we can go about ahead and say next is in this description, or oftentimes what you'll see written in questions or in real world interpretations, is that you might have, say, something like a ball that fits perfectly inside the box. And by perfectly, we're meaning essentially that the bottom surface of the box contacts the circle, the sphere. The bottom of the sphere contacts, obviously sits in the box, but the top of the sphere touches the top of the box, so it's nicely packed inside there, almost like you purchasing like a soccer ball from the store. What this means essentially is that the height of this circle, or what we could possibly call the equator of the circle, as in that longest circumference around the sphere, is also going to be 8 centimeters tall. So we know for the sphere, we have 8 centimeters equal to our, what we can say is our diameter for the circle. One question you'll often see is, okay, you have these two objects. What is going to be essentially the negative space, or that empty space that exists, that vacuumous area that's going to be around the ball where there's no cube? To go about figure out an equation like this, we have to do multiple steps. Similar to the examples where we saw like a cylinder on top of, say, a rectangular prism, we had to add them together. In this example, we're going to remove the sphere from the volume of the cube. So essentially, we're going to set up like a subtraction equation. The first thing that we have to do is find the volume of the cube. So we find the volume of our cube. The volume of our cube is equal to the length times the width times the height, or 8 times 8 times 8, or what we would properly call 8 cubed. If we go ahead and solve for 8 cubed, we end up having a value of 512 centimeters cubed. Okay, so we got our first answer. That's going to allow us to solve for just the physical box itself and how much space it takes up. Next, we want to find the value of the sphere itself. So our equation, once again, for a sphere is going to be 4 over 3 pi r cubed. And we're just going to go ahead and insert our values here. We have 4 over 3 times pi times, it's not going to be 8. But for this particular example, our radius is going to be 4 because we're going to divide that height in half, or that diameter in half to get our radius. So we're going to say 4 cubed. Okay, next up, let's keep on going forward. Couple things that we can do here. 4 cubed, 4, which is 16, times a value of 64. If we want to keep that fractional option, we can do 64 times 4 if we'd like to do that, which is 256. In this particular example, the method that I'm going to go with, or I think makes most sense, is to convert it into a number that's going to be similar to that just straight up 512. We're going to actually calculate that value of pi, actually calculate that fraction out. If we go ahead and input these values into our calculator, of 4 over 3 times pi times 64, we end up getting a final value of 268.08 centimeters cubed as our volume for this sphere. Volume of the sphere. So now we have these two values. The third thing that we're going to do is just find the difference between the two. So we're just basically going to take the sphere value, or sorry, the cube value first, We're going to subtract the sphere, and that's going to be our empty space. Okay, so now we take our value, 512, going to subtract 268.08, and we're going to get a value of 243 centimeters cubed as our final answer. To go about reviewing this notion of the sphere, we just have to kind of start once again with our circle definition, where all points that exist on the circumference are going to be equidistant from that center point, which is essentially our radius. When it comes to a sphere, we're dealing with the same concept, but in a three-dimensional manner. All points that exist on that exterior portion of our ball, exterior portion of our softball, if you will, or soccer balls, and so on and so forth, are all equidistant from the center point. If we're going to add an additional term or two on top of that, we have concepts as opposed to just the diameter, which is a straight shot right through the sphere itself. If we talk about the term equator, equators can be the portion that goes around the circle itself at the largest circumference. So the equator is essentially directly in the middle of the ball. It's not going to be on the top here because, as we saw with our cross section, those circles that get formed are relatively or considerably smaller than the one that's directly in the center. So our equator is going to go in the middle. Considering our planet Earth, it's oblong spheroid. It's not actually a ball, but slightly crunched near the center or the equator. That's why our equator goes left and right versus what we normally see on a map would be from the North Pole to the South Pole. So that's it for today. As always, you have online classes today. If you want to come in and check me out, they start at 1:05. If you have any late work, please feel free to email me. Any questions, things like that are always, always, always welcomed. Until next time, I guess see you back in September. Stay safe. Bye.